Hey there, guys. So as most of you know, I am a high school math teacher, and all these videos I make during class. Well, I've been getting some questions recently about reflections that happen somewhere other than an axis. Okay, so we have the idea of an x-axis reflection where the points go from top to bottom, right? And what happens with an x-axis reflection is the x value stays the same, but the y values change, right? This is like the point 2, positive 3, and this down here would reflect to be the point 2, negative 3. Okay, or what happens on a y-axis change, so this is your y-axis, so this point would mirror over to here, would reflect over to there, and our x value would change and our y value would stay the same. So the x changes and the y stays the same on a y-axis reflection. Okay, and my students are asking me, well, what happens if it's not on an axis, right? What happens if the reflection happens at the line like y equals 2 or something? So here's the horizontal line, y equals 2. Okay, what happens if this is your axis of reflection, right? What happens to these points? And is there a rule, right? Is there a rule that I can come up with in order to make this easier for me to do? Okay, so we're going to explore that idea today, is finding a rule that comes up with a reflections other than an axis. So this is the line y equals 2. We'll look at that one, and then we'll look at an x version or a vertical version of this in a second. Okay, so I want to get down to the nitty-gritty about what's really happening here as we do these reflections. Okay, so let's consider the point 2 comma negative 1. Okay, so if I was going to reflect the point 2 comma negative 1 across the line y equals 2, right, because this is a congruence transformation, the distance that my point is away from that line of reflection, in this case that distance is 3, needs to be the exact same as the distance that it becomes reflected at, right, on the other side of your line of reflection. Okay, so that's what it means about congruence. The distance that it is away from your line has to be the same as when you reflect it. Okay, so in this case, our point would jump up here to, let's see if it's at negative 1, 0, 1, 2. It's going to be 3 units above positive 2, which is at 3, 4, 5. So this would be at the point 2 comma 5. Okay, now what if I wanted to write a rule so that I could translate maybe this triangle, right, this random triangle here, with one equation, right? What can I do to all of these points in order to make them be able to calculate rather which how the reflection is going to go? So I want to find and generate a rule. Okay, so the things that stay constant are our y value, right? We always have a y equals 2. And also the distance that our point is away from that line of reflection, right? These are all kind of constants. Well, I guess they change depending on where your point is. But what happens is, of course, the reflection distances stay constant. So if this point here, which we're going to call, we'll call this point 5, negative 2. Right, so this point is 4 units below our line of reflection, so it's going to end up 4 units above your line of reflection. Right, those things are constant. So the distance from point to point is always twice the distance between your point and the line of reflection, right? This distance. From point to point, that always gets doubled. Okay, so that's something that always happens, right? This one from point to point is double the distance from our point to the line of reflection, right? This distance is double. So this doubling idea is always staying constant. So then how can we calculate this, the distance between your line and the point? Okay. Well, distance is right, y minus y over x minus x. And since the x values here are the same, those are going to actually cancel out. So your distance is always found by taking your line of reflection, right, the actual line value, and subtracting that y coordinate from your problem. Okay, so let's see if this works for at least these two. Okay, what is positive 2 minus negative 1? Well, positive 2 minus negative 1 is 3. Perfect. What is positive 2 minus negative 2? Well, 2 minus negative 2 is 2 plus 2, which is 4. Okay, so this seems like a pretty good rule that I have generated, that I can figure out how far any point is from that line of reflection. Okay, so that's what I'm going to put in here. Right? As we're generating this equation, I have double the distance between my line of reflection and the y value. Okay, so let's put some notation, some notes in here. Okay, this is your line of reflection value. Right, so this is the y equals 2 part. Right, because y equals 2 isn't always going to be your horizontal line of reflection. So this value will change based upon your problem. Okay, whatever your horizontal line of reflection is. So this tells us the distance that any point, the distance between our points. Right, so this is the distance between, there's a shorthand, between your image, right? So your image is the point after your reflection. This is your image point. Between your image and your pre-image, which is, of course, the original value that we started with. Okay, your pre-image is the point that we start with, and the image is what we get. So that's the distance between the image and the pre-image. Okay, a pretty important idea. But now we have to decide, where are we starting from, right? We have to add this to some starting value. Where are each of our points starting from? Well, this one started at negative 2 in the y value. This one started at negative 1. This one started at 0 minus 3, so it started at minus 3. Okay, so it looks like our starting point is always going to be the y value from your problem. The y value from your problem. Okay, so this is a pretty good idea, or pretty good equation that we're going to try and incorporate into our general rule, right? Our general rule, our notation for being able to write any point that gets reflected across the line y equals 2. So let's do a little bit of algebra and simplify this, shall we? So I'm going to distribute this 2. So I'm going to multiply this 2 into both of those equations there. So I have the y on the outside plus 2 times 2 is 4 minus 2y. 2 times 2 is 4 minus 2y. Okay, and since there's really nothing going on, I can take away these parentheses pretty easily, so I can combine my like terms. And I get a simple equation of 4 minus y. So if I'm looking for a rule, right, between my pre-image point and my image point, okay, I notice, of course, that the x value doesn't change, and that happens always with a vertical transformation, okay, with a horizontal line of reflection. So my rule might be the x value doesn't ever change, but then the y value is 4 minus y. Okay, so this is a pretty simple equation, and that's what we want. We want some simplistic equation, not something complicated, right? This is pretty complicated up here. Okay, it's got a lot of parts to it, and circles and colors and all that other good stuff. So let's see if that works for any point. Okay, so let's pick a random point. Let's pick the point over here, negative 1. So let's do one above. Let's say right here. How about this point at negative 1, comma 1, 2, 3, 4, 5. Negative 1, comma 5. Okay, let's see if this rule will work for negative 1, comma 5. So if I'm going to use my counting method, that's 3 units above the axis, which should end up at 3 units below the axis. We're expecting it to be at negative 1, negative 1. Okay, so let's see if we can apply that. Our x value is negative 1, and our y value is 5. So we're going to replace we're going to replace x with negative 1 and we're going to replace y with 5, and we're going to do this subtraction. 4 minus 5 is negative 1, and sure enough, that is where our point ended up. Okay, and you're saying, sure, Manch, but that's a pretty easy one. How about we do one more difficult? How about we do 3, negative 3, 4, 5, 6? How about we do this point here at 3, negative 6? Okay, and let's calculate where it should end up. Okay, remember the x value doesn't change, and we're going to subtract the y value. So our y value is negative 6. So 4 minus negative 6, we are expecting this to end up at 3 comma 10. 3 comma 10 is where we're going to try and find it. So let's see if that actually works. How far away from our line is negative 6? So it's 1, 2, 3, 4, 5, 6, 7, 8. It's 8 units below our line of symmetry, so we're going to count 8 units above. 2, and then we have 1, 2, 3, 4, 5, 6, 7, 8. So here's where we're expecting that point. So here's 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure enough, this ends up at 3 comma 10. Okay, so our rule is a pretty good rule, right? It works pretty much every time. Well, you know what? This is not anything too special. Okay, this value is really what we're looking for. Okay, so if you notice, we had the line y equals 2 as your equation. Well, this value here is always double your line of reflection. Okay, so if we were going to do a horizontal y equals some value a, right? A is the y-intercept, the horizontal line value. So for some random value y equals a, our general equation would be x comma a minus y. Nope, sorry, that's not right. Let me erase that. My brain just did a little funky thing there. It's not the same as your a value, it's twice your a value. Okay, because we had a y equals 2 as your horizontal axis, and then the 4 became doubled. So we have the equation x comma 2a. We double your value for your horizontal line, and you subtract the y value from your any given point. Okay, so this is your rule if we have a vertical reflection, aka a horizontal line of transformation. And I meant line of reflection. Sorry, I said line of transformation. So that's your rule. We're going to double the horizontal line of reflection value. Well, you know what? What if we had a vertical line, which is a vertical line of reflection, which is a horizontal transformation, right? Like an x equals or something like that. So if we had a vertical transformation like x equals 3, a vertical line of reflection is a horizontal transformation, a horizontal translation, a horizontal reflection. Well, it turns out that the same thing happens. We double the a value, which is, right, x equals a, is the equation of your vertical line. We double that, and we subtract the x coordinate from every point, and the y value stays the same. Okay, so this would be your rule, or the notation that you get if you have a vertical line of reflection. Okay, so this is in general what we're going to do if you have a line of reflection other than your x-axis or your y-axis. Okay, so it's not as easy, right? It's not as easy as these ones where they simply switch positions, right? There's a little more involved, but I think you're smart enough that you can do it. Okay, so hopefully that helps. I know it will help my students as they continue to work on these general rules and notation for geometric transformations.